This is Lesson 3.7, Apply Displacement Map and Perspective Transform. Let's begin with the Displacement Map effect. Displacement Map lets you displace or move pixels from an input source to an output destination. To do this, you use a 2D map with offsets and scale factors. Specifically, the Displacement Map effect displaces pixels for an input source location to a different position in the output destination. Here are the properties. mapData, which determines how to map the pixels. Offset X and offset Y. These properties are fixed displacements along the XY axes applied to all pixel offsets. Defaults are 0. Scale X and Scale Y. These properties are scale factors along the XY axes that are applied to the map. Defaults are 1. Wrap, which wraps the displacement at the boundaries if true. The default is false. And last, the input property, which is used for chaining effects. Now you can see that the displacement map uses a 2D map specified by the mapData property. So let's tell you more about this property and how the map works. The mapData property lets you control how pixels are actually moved from an input source to an output destination. To move the pixels, a two-dimensional map is necessary, and the map conforms to this equation. Now it's a bit easier to see how all this works when the offsets are 0 and the scale factors are 1, which are the defaults. But the general idea is that pixels for X and Y locations are moved from the input to the output using separate offsets and scale factors for X and Y. The offsets represent the distance between the destination pixel and the source pixel, and the scale factors apply to the offsets and increase or decrease the effect. Note that pixels are displaced relative to the top left corner of the output. That would be the 0 and 1 notations that you see here. Source width is the width of the input source and is used to displace the X value. Likewise, source height is the height of the input source and is used to display the Y value. And FloatMap is used for the actual 2D map implementation, so let's show you this class next. FloatMap is a support class that lets you create 2D maps of XY sample data. FloatMap also supports a band concept, where band 0 is used for the X offset and band 1 for the Y offset. Here are the properties. Width is the width of the map in pixels, and height is the height of the map in pixels. Both properties have a range of 1 to 4096 with a default of 1. Now to load the map, use these methods. setSample, which sets values at XY locations for a specific band, and setSamples, which is overloaded to set values at XY locations for up to 4 bands. Okay, let's show you a JavaFX program now that uses a displacement map. This is the MyDisplacementMap program, which creates a displacement map effect for a text shape. Let's compile and run this program and examine its output. What you see is a bold red text string with a wavy appearance, all on a light yellow background. Let's show you the JavaFX code for this program now. First, the program creates a float map with a constructor that sets the width of the map to 220 and height of the map to 100. The two loops fill the float map with the displaced pixel values. The outer for loop iterates over the map width, and the inner for loop iterates over the map height. The invocation of math.sign here creates the wavy appearance for each pixel width denoted by pixel row I. We divide by 30 and multiply by pi so that we get a complete wave over a 30 pixel space. And we divide each value by 10 to produce values in the range -0.1 to 0.1, which reduces distortion. The call to map.setSamples loads the map I sub j location. The 0 value means coordinate x doesn't change. The y coordinate is set to the math.sign value. This statement creates the displacement map object and loads it with the float map. Next, the program creates a text object at 65,110 with the text string. The setters set the font to bold Tahoma with point size 50 and a firebrick red fill color. The call to set effect applies the displacement map effect to the text object. And here's where we add the text object to the root scene graph. Let's experiment with this program now and modify the displacement map effect. First, I'll change the scale Y property to 0.3 with this statement. When I recompile and run the program, you'll see that the text string is much less wavy. And if I set the scale Y property to 2, when I recompile and run the program, you see that the text string doesn't look so groovy anymore. Scale factors can also be negative. Let's change scale Y to -1. When I recompile and run the program, you see that we have reversed the effect of the map. In the original program, the wave goes up here and here. In this program, it goes down in the same spots. So as you can see, DisplacementMap lets you control how to render pixels with 2D shapes and images. The next effect is PerspectiveTransform. This effect gives 2D content a three-dimensional look by creating perspective views in the z-axis direction. Now, PerspectiveTransform is fairly easy to set up and use. However, the effect does not guarantee that lines parallel in the source will necessarily be parallel in the result. Here are the properties. LLX and LLY. This moves the lower left corner of the input to these x and y coordinates. ULX and ULY, which moves the upper left corner of the input to these x and y coordinates. LRX and LRY. This moves the lower right corner of the input to these x and y coordinates. URX and URY, which moves the upper right corner of the input to these x and y coordinates. All coordinates default to 0 if not specified. And last, the input property, which is used for chaining effects. Now, to better show you how to use these coordinate properties, let's explain how this all works. This is a diagram that shows you how to specify the coordinates of a perspective transform effect. The box shown is the original input source. Around the z-axis, shown here as a dotted line, we move the endpoints of the input source. And here's an example of a perspective transformation. This is the upper left corner, denoted by the ULX-ULY notation. And this is the lower left corner, denoted by LLX and LLY. The upper right corner is URX-URY, and the lower right corner is LRX and LRY. The thick lines show how the input source would be drawn using these coordinates. And the perspective transform effect takes care of all the messy details that render this perspective for you. Okay, let's show you a JavaFX program now that uses a perspective transform effect. This is the MyPerspectiveTransform program, which creates a perspective transform effect for rectangle and text shapes. Let's compile and run this program and examine its output. What you see is a 3D perspective of a bold red text string inside a dark blue rectangle, all on a light yellow background. Let's show you the JavaFX code for this program now. First, the program creates a perspective transform object with the default constructor. These setters set the perspective coordinates. In this example, the upper left corner is at 50, 100. The lower left corner is at 50, 175. The upper right corner is at 450, and the lower right corner is at 400, 250. Next, the program builds a rectangle object at 120 with width 305 and height 100. The setter sets the rectangle's fill color to dark blue. The program also builds a text object at 120/80 with a text string. The setters set the font to bold Verdana with 40 point size and fill color red. And finally, we add the rectangle and text shapes to the root scene graph and then apply the perspective transform effect to the root. This adds perspective to both the text string and the rectangle. Let's experiment with this program now so that you can learn more about the perspective transform effect. First, I'll change the lower right LRY coordinate to a larger value, 350. When I recompile and run the program, you see a bigger perspective. Next, I'll put the old value for LRY back to its original value and make the lengths shorter. To do this, I'll change the upper right URX coordinate to 250 and the lower right LRX coordinate to 250, both smaller numbers. When I recompile and run this program, you see a shorter perspective.